So this is a picture of a hydrogen atom. And if you will zoom in really close, we have a person sitting in the nucleus looking up at that electron. And so they're looking upwards. And if you could freeze that electron in one position, you would see that the electron could be here. That's where it is. And if it was really excited and jumped up, it could be there, 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 or there. Yes, we're still saying it's spiraling, but because we don't want to spend the time to draw this absolutely amazing picture here, we have a shortcut way of how we represent all these circles and everything so it doesn't get so confusing. So what we do is, like, since looking up, they will just see it's like a ladder of levels. That's what we write to make this make sense. So over here, this level right here, that is our first level, n equals 1. So this is like our 1 orbit. That's our first orbit. And then up here we have n equals 2. That's our second one. 3, that's our third. 4, that's our fourth. And this is our fifth. So you can see, like, we're not saying that all of a sudden we're like in this ladder. I mean, there are still the circles, but it's just so much to draw it all. So this is how we represent this information. So as we begin, we have these different circles, and Bohr says, okay, I've got a number, and this is the energy the electron has to have when it's in this orbit. This is the energy the electron has to have in this orbit. It's this energy and then this and this. So that's what it is. And the farther out they get, the higher and higher the energy. You'll notice this is negative energy. That could be confusing, but this part of the atom, this is lower energy, and as you move out, you get to be higher and higher energy. You can almost think of this as the farther you away from the nucleus, the more you can do your own thing, and the electrons have a lot more freedom really far away. You can think that way too. And eventually you can get so far from the nucleus, if he gets too much energy, that electron can pop out of the nucleus. So what excites an atom? Well, there's lots of things. This example here is pretending that it's sunlight. So we have our unexcited atom with our electron in the n equals 1 position, and sunlight comes in. Now, sunlight is white light, and it comes with all different frequencies. So you might have, a really, really small frequency. You might have a really broad frequency. So it comes with all of these different wavelengths. White light is basically light that has all different wavelengths all mixed in. It's like the full, rainbow spectrum is all in there. So this wavelength would maybe pass through the electron and absolutely nothing would happen. But if you catch just the right wavelength, it gives it just the right amount of energy. This electron here, we're going to draw it over to the right. What might happen is that his space where he was will become empty, and he'll jump up to the n equals 3 position. You can think of this like giving a child way too much caffeine. So they're up in that position and they're really, really fast and they're moving really fast. But like everything in chemistry, low energy is best. So they do want to go back down to their original state. So we always have that electron going back to the non-excited, the unexcited atomic state. So that electron will end up leaving this position and he will drop back down. How does he do that, though? He has all this energy. He absorbed this energy, and he drops back down. By the way, he could also just drop to here. Why don't we have him drop to here and then drop to here? So he could drop in all different ways. He doesn't just have to drop to the very lowest spot. So how does he get from here to here? He does it by releasing that energy he absorbed. So over on this side, he absorbed just this one frequency of sunlight. He jumped up, and while he's up here, he's still holding on to all of that energy. But he doesn't want it, and so he gives it away as a wavelength. It should be a straight line, but he gives it away, and when he gives it away, then he can drop back down to his original position, which is low energy, which makes him happy. Here's the super, super cool thing about all of this, and it explains why those different tubes were glowing all these different colors, is that if that wavelength is the right separation, meaning the separation that falls in the visible spectrum, you'll see it as color. So up here in that picture up here that we were showing of these tubes, the electrons were jumping down from having been excited because electricity is passing through the tube, exciting the electrons to all the different levels. Helium has 2 electrons. Neon has 10 electrons. All those electrons are all jumping into all the other levels. They can't jump into a level that's already full. So sometimes they have to kind of, wait their turn. But this is continuously happening. They're continuously jumping, continuously dropping. And so what you end up seeing is this color that's coming out, and it's really, really pretty. And that is, as they're dropping down, they're releasing their energy. And that release is directly related to the difference between the different energy levels. So this distance, or this distance, or this distance, or this distance.